So let's start with tabular data. And this is usually the type of data that we are used to before moving towards more complex data like speech or images or text. But what is a tabular data? There is usually a scientist or somebody who is an expert in their own field who are going to be collecting data. For instance, there is this scientist who was studying flowers, in particular iris flowers, and they were doing measurements of the sepal length, sepal width, petal length, petal width, and they were collecting that data. Some of the flowers are of type of versicolor, some of them are setosa, some of them are virginica. So you have 3 different classes of or types of flowers. And the scientist would create a table or an Excel spreadsheet or a .csv file with 5 columns, 1, 2, 3, 4, 5. And these are going to be the variables of the model, of the data. And these are the features. For instance, one of the flowers had a sepal length of 5.5, a sepal width of 2.5, a petal length of 4, and petal width of 1.3. And the corresponding class is versicolor. Some of them are virginica, and they have different measurements. So each row is going to be an observation. Each column is going to be a feature. And the scientist collected 150 observations, and you have 5 variables. Now let's say we don't want to call the scientist again. We already paid them enough, and maybe they're busy. They're not willing to give us 151 data point. They're not willing to do the measurements. Maybe it's too expensive to do the measurements. What you can do is you can build a model and try to predict. You go ahead and do your own measurements of a flower. Somebody comes to your office with a flower, and they have some measurements. They're going to say, I have the sepal length of 5.2, a sepal width of 2.3, and 3.7. You get the idea. And maybe 2 here. But I don't know what species this flower corresponds to. Can you tell me? We have 2 options. One is call the scientist again and ask them. The other one is we just build a model that's going to do the prediction for us, which should end up being much cheaper. So that's the idea. We want to do classification on new data, on new observations. I know some of you have taken statistics course in the past, but this course is going to be about machine learning and deep learning. What are the differences? The goal of statistics is to come up with a model that explains the data. So they have some data and they want to explain its predictions, look at the weights of their model, and decide how important one of the variables is for that particular prediction. What is the confidence interval? How sure are they that their estimates are correct for the parameters? What if they have a hypothesis, a null hypothesis? Can you accept it? Can you reject it? So these are the sorts of analysis that you see for statistical models, but this is a machine learning course. What is the core? What is the objective here? You want to come up with an algorithm, and sometimes I'm gonna interchangeably say algorithm and model. You want to come up with a model or an algorithm that performs well on some test data. So that's your objective. So you have different goals. These 2 fields, statistics and machine learning, they have different aims. They have different objectives, but they might be using similar tools. The tools may be similar, but they have totally different objectives. One of them is trying to do prediction and basically try to replace the scientist. That's the idea with machine learning. Now that you want to care about only the test data, and these are the new data that you see, you need to try to mimic what's going to happen in the reality with test data and training data and validation data. So what you're going to do is you're going to divide your data set, maybe this 150 observations, into 3 different classes. Some of them are going to be training data. Some of them are going to end up being validation data. And some of them are going to be ending to be test data. So the ones with a prime, they are validation. The ones with double prime, they are test data. And the ones without any primes is just the training data. Let's say you keep 100 data points to be your training. You keep maybe 30 data for validation, and maybe 20 data for testing. And the final objective is you want to have an algorithm that you put it in production. Somebody gives you new measurements and you just predict. And you want your algorithm to perform. What do we mean by performance? What is our metric? Maybe accuracy is a good metric. There are many good metrics out there, and actually many bad metrics. But as soon as you choose a metric, you're going to be able to look at a model and try to measure its performance. You pick an algorithm and you are trying to measure its performance on the test data. What are we seeing here? F of alpha and beta is a model, is an algorithm. It is parameterized by alpha and beta. And I'm going to be more specific by the end of the slide. What is alpha and what is beta? What do I mean by them? But let's say somehow magically you have this F of alpha and beta. Now you want to measure its performance. You can take X, push it through F, and that's going to give you a prediction by hat. For the sake of argument, for now, let's say alpha is your hyperparameters. We don't know yet what I mean, but let's say they are hyperparameters, and beta are the parameters of your model. So your model is parameterized. Some of them are hyperparameters, some of them are parameters, and I'm going to define them soon, so don't worry about it. But we don't care about any alpha and beta because that's going to give us a huge family of models to work with. We are interested in a single algorithm. We're interested in an algorithm. So we are interested in perhaps the best one, alpha star and beta star. So this is our best model that we could come up with. It's going to make some predictions. And we said we don't really care about the training and validation. We just care about the performance of the model and new data that it sees on test data. And our test data was double prime. So you take a test data, you know the corresponding ground truth. For your test data, you know the prediction of the model on the test data. Now you can look at, for instance, a measurement like accuracy. You count, this summation here is going to count the number of times that the algorithm is correct, is making a correct prediction. When the prediction matches the ground truth, this function is going to be a 1. Otherwise, it's going to be a 0. As soon as you do a summation over your entire data, you're going to get the number of times that your algorithm is correct divided by the number of times that your algorithm is making a prediction on the test data. That ratio is going to give you the accuracy. It's a performance metric. So I know there is a question in the chat, what is the difference between validation and test? That's exactly the purpose of this slide. So I'm going to go through every single detail so that everything is clear. So I'm going to answer your question shortly. Does that sound good? Okay, perfect. Now we have a performance metric. Now you know what I mean by this sentence. You want to come up with an algorithm. This is our algorithm, and you want it to perform well. What do we mean by perform? This is the exact definition. You pick a metric, for instance, accuracy. That's going to give you the performance metric, and you want to evaluate it. You want to know how accurate your model is on some test data. So we know what is the purpose of testing for now. But what is our model? I'm going to step by step try to expand upon what we mean by a model, what we mean by an algorithm. For now, f of alpha and beta is just picking out the minimum, actually the maximum, I'm making a mistake here, is the argmax of this probability. So the class with the highest probability, we are reporting that. And p alpha beta x is a probability vector. We are picking out the jth element of that probability vector, and then we are doing that argmax on top of that. Okay, so far so good. And because we want it to be a probability vector, it has to add up to 1, and it has to be positive, or actually greater than or equal to 0 for it to be a probability vector. As soon as you have a probability vector, I'm not telling you what the details are yet. I'm going to tell you next by the end of the slide. But as soon as you have this vector, you can pick out the maximum element, and that's going to give you the prediction. For instance, in this case, these are my questions for you. What is K for this particular problem on the left for this data?
150.
3.
5.
3.
So yes, K is going to be 3 because you have 3 classes. You want to choose between versicolor, setosa, and virginica. K is going to be 3, N could be 100, N prime could be 20, and N double prime could be 30. Okay, so you're just dividing your data that way. What is D in this case?
So 4.
Yes, so D is going to be 4. These are your variables: sepal length, sepal width, petal length, petal width. So D is 4. X is going to be this vector, for instance, 5.5, 2.5, 4.0, 1.3 could be an element of your data. I is indexing the rows, and Y is what you're expecting out of your algorithm to classify. You want an integer to come out. Is it class 1? Is it class 2? Or is it class 3? And you're associating an ID. This is class 1. This is class 2. That's class 3. What you're doing now with this P of alpha, beta, which is going to be a vector, you're outputting a vector that has 3 dimensions. Maybe it is 90% sure that your class is a versicolor. It is 10% sure that it's a setoso, and it's 0% sure, or it's 0% certain that that's going to be a virginica. What you're doing here with this argmax, you're picking out the maximum for your prediction, and that's going to be class 1. So now, is everything clear in terms of the model? Any questions? I still owe you what is validation data, why do you need training data? I still owe you what are the details of P. I'm going to give you that. But for now, assuming that you have a P, you know what your model is doing. It's picking the maximum probability. Is everything clear?
Yeah.
Yes.
Okay, perfect. Now it's my time to give you all of these details: training, validation, and this P. For training, what do you want to do? You have some data and you have some model that you somehow came up with, which was P of alpha, beta, giving you some probabilities. What you can do is you can try to increase the probability of the correct class. In this case, Xi could be 5.5, 2.54, and 1.3. The corresponding class is versicolor, it's class 1. So you're going to put a 1 here, you're going to put X here, and that's going to give you the probability that is associated with that class. And that's going to be maybe 0.9 coming out of the model. And you want to increase that. Once you take a log of a number that you're trying to maximize, it's the same thing. Log is an increasing function, so it's not going to change anything. You're still maximizing that probability. In machine learning, it's a convention that we usually like to minimize, so you multiply by a negative sign. If you minimize this loss function, you're maximizing your probabilities. You're maximizing your likelihood. And likelihood is just your probability evaluated at your data, because this probability could have been yi could be anything, could be 1, 2, 3. Xi could be anything. But now you are specifying it. You're saying that on this value for this particular input data, I know the corresponding value for the output data. Increase that probability for me. Make it more likely. Now that that's happening, there was a constraint here that these probabilities, they have to add up to 1. If you have a bunch of numbers that are positive, you increase one of them, they have to add up to 1. So the other 2 have to go down. So this is a very nice loss function. As soon as you increase the probability of the correct class, the probabilities of the other classes are going to go down. So that's going to give you your loss function. And this summation here is coming out of your observations. These observation 1, observation 2, observation 3. You're assuming that they are independent. They have identical distributions. So they are IID. Once they're IID, the probability of the entire training data is going to be a product of the probabilities of individual ones. And that's why you're taking a log. Log of the product is going to give you the summation of your logs. You take the log to turn the product into a summation, because working with summation is more stable. When you multiply a lot of numbers together, there are 2 scenarios that could happen. They're either all less than 1 or bigger than 1. In this case, it's not going to happen. They're going to be less than 1. And as soon as you multiply a lot of numbers together, they're going to go to 0. Or if they are positive, bigger than 1, it's going to explode. So we have a problem with multiplication. Summation is much nicer. And that's why you take a log. And what are we trying to do? What is the purpose of training data? Why do you do that? Because given one alpha, I still owe you what is alpha. It's going to be clear soon. But if I give you alpha, if as soon as you find a minimum value or the minimum argument of your loss function, that's going to give you the correct parameters. That's going to give you B star. And that's the role of training. You want to find among this family that we defined, among the family of models, you want to pick the best that is performing the best on your training data. So is the role of training data clear now? Are there any questions about the loss function and what you're trying to achieve through training? Any questions? Okay, perfect. Now your question is, what is alpha and why do you need validation? Alpha are the hyperparameters of your model, and let's take a look at it. We know that if I give you alpha, you're going to do some training on the training data and you're going to give me B star. So B star is a function of alpha. Now you go ahead and evaluate your model on your validation data on X primes. Look at the predictions, compute your performance metric, which in this case is the accuracy. So it has nothing to do with your loss function anymore. This is your performance metric. And then you want to choose the best alpha. So the role of validation is to choose alpha or the best alpha. The role of training is to find the best beta. And as soon as you do that, you're going to end up with a model or with an algorithm that you can put it in production. But before you put it in production, you have to make sure that things are correct. So you look at your accuracy on the test data. I still owe you something. What do you mean by alpha and beta? Let's take a look at a model, maybe a multi-layer perceptron. So yes, Sabrina, you're right. This has to be, again, argmax. You are maximizing the accuracy. So I have two typos in this slide. One is this argmin. It has to be argmax. This has to be argmax too, but this is correct. You are minimizing the loss, you are maximizing your accuracy, and you are maximizing the probabilities to do your prediction. So this has to be a max, this has to be a max, and this is still min. So I'm going to correct that. But for now, we want to know what is alpha, we want to know what is beta. So I kept it open for a while. Let's close that gap. Let's write a model. Let's say I'm going to take x, which is a vector in dimension 4. I'm going to multiply it by a matrix. It's going to take you from dimension 4, perhaps to dimension 100. So now my question is, what is the size of V? Out of this operation, I want to go from dimension 4 to dimension 100. What is the size of V?
4 by 100.
Yes. So it's going to be, because you are multiplying from left, it's going to be 100 by 4. And then the outcome is going to be 100 dimensional. You're going to add a bias. It's a vector, which is going to be 100 dimensional. You're just adding these two together. And for those of you who know linear regression, this is just doing linear regression. It's very similar. Then you want your function to become nonlinear. You apply a nonlinearity, such as ReLU. ReLU is just the maximum of this value and 0. So it's going to be linear on the right-hand side of your curve, and it's going to be 0 on the left-hand side of 0. And this is to make your model nonlinear. Otherwise, if you remove this, then things are going to end up being linear and boring. Okay, now we are in dimension 100, and this ReLU is going to act element-wise. So in deep learning, we are going to do a lot of element-wise operations. If you have a vector, you look at your first entry, you find a maximum of your entry and 0. That's going to be your output. Then you look at the second value, the second entry in your vector, maximum of that and 0, you report it. So the outcome is still going to end up being a vector. A vector goes in, a vector comes out. And you're just making your numbers positive. And if any of them are negative, you zero them out. That's your H. So what is the size of H? So it's going to be in a vector that is 100 dimensional. Okay, a 4-dimensional vector goes in. You multiply it by a matrix that has a size of 100 by 4. That's going to end up being 100 dimensional. ReLU is going to keep the dimension. So H is in dimension 100. Okay, it's a 100 dimensional vector. Now what you want to do, you don't care about 100 dimension. It's too much. In the end, you want to output 3 probabilities. You want to output 3 values for versicolor, setosa, and virginica. You want to go from dimension 100 to dimension 3. How do you do that? What is the size of W now?
3 by 100.
Yes, exactly. And what is going to be the size of B?
Which is 3.
Yes, exactly. And after that, you're going to end up with three numbers that are from negative infinity to positive infinity, but you want to get out of it a probability. What you can do is you apply this softmax function. So what I want you to do is right after the class, this is an exercise, look at the definition of softmax. So just Google it. It's going to turn a bunch of numbers, three numbers that are from negative infinity to positive infinity, and it's going to turn them into probabilities that add up to 1. So there is a question, how do we determine the vector v? V, first of all, is not a vector, it's a matrix, but your question is a very good one. How did you choose 100? So we understand 3, yes. You have 3 classes, k is 3, we understand that. We understand the size of x, we understand 4, because you have 4 input variables, 1, 2, 3, 4. But where did you come up with 100? Why 100? Why didn't you go to dimension 1000? Or why didn't you go to dimension 256? What is magical about 100? The answer is there is nothing magical about that number. That's your alpha. The choice of the size of the hidden layer, this is your hidden layer, hence the name, we are using the letter H, so that's your hidden layer. The size of that, you're gonna choose. It's something that you choose. It's a hyperparameter. It's your alpha. The other thing that you choose is you can keep doing this over and over again. You can take x, multiply it by v, apply rel u, multiply it by w, apply rel u, keep doing that, and make your model deeper and deeper. This model is 2 layers deep. We can make it 5 layers deep. That's also alpha. That choice is also alpha, is your hyperparameters. And we know how we choose them. We choose them based on the validation data. Now, my question is, what is beta now? Beta, the answer that you're giving me is W is beta. It's more than that. So these are exercises. What do you think beta is going to be? Exactly. So it's going to be the weights and biases. So it's going to be, you are right. W is one of them. It's a list of W, V, A, and B. These are the parameters of the model. Alpha is the depth of your network, is the width of your network. Beta are the actual parameters, are the weights and biases. So now you know how you set them. You pick an alpha, you say, let's say I want a 2-layer deep neural network with 100 units. You pick that. Then as soon as you pick that, you're going to be able to optimize over the parameters of your model by training, by looking at your training data. Now that you looked at your training data, you find beta star. Then you go ahead and say, maybe I need to change alpha. Maybe my network needs to be deeper, or maybe it needs to be wider. And then you keep doing that for multiple choices, and then you pick the best model, and you report its accuracy. And there was a question about, is rel u of x equal to maximum of x and 0? The answer is yes. Am I answering all of your questions? No? Any new questions?
I actually have one question. How do you normally choose to change alpha? Is there like a specific, is it problem specific, I should say?
That's a good question. Actually, I need to also tell you, how do you solve these minimization and maximization problems? How do you solve them? I know that I'm assuming that there is a way to solve it, but how do you actually solve it? And that's actually for the entire course that's in front of us. So what I want you to do next is click on this link when you are at home, right after the class, watch the video for optimization algorithms. This is going to help you choose beta. So the theta that you're seeing here is exactly the parameters, is exactly these betas, are these weights and biases. And you're going to assume that you know alpha. Now your question is, how do you actually find alpha? Maybe this one, we are going to watch a video and we are going to learn how to do it. But how do you actually find alpha? How do you solve this maximization problem? And as you can see, this is a discrete objective, discrete value objective. So you cannot just take gradients with respect to alpha, because alpha was a discrete choice. I want a 2-layer deep neural network with 100 units. It's not like I want a 2.5 deep neural network with square root of 144 or 143 neurons. And then you cannot take gradients. So you cannot do gradient descent here. And there are multiple ways of solving this problem. When we go to AutoML, automatic machine learning, It's one of the topics that we cover. We are going to see different ways of doing it. One of them is just random search. The other one is just grid search. You put a grid on alpha and beta and you do grid search. You find the best accuracy. What else? There is, you can do reinforcement learning type of algorithms. And then you can do genetic algorithms. So when we go to AutoML, that's exactly what we are doing here. And there is a question is asking, alpha is part of beta? Not really. Alpha is totally separate from beta, but as soon as you choose alpha, you are going to be able to optimize for beta. So the second part of your question is correct. You first choose alpha, you first say, I want a deep neural network that is 2 layers deep, 100 neurons. Now I want to find the best parameters. And as you can see, this process is really slow because for each alpha that you pick, you need to train your model from scratch. And that's why topics like AutoML, you see them being the state of the art being pushed by these giant companies like Google, Facebook, Amazon, because they have the resources to do that, to train big models multiple times. So does this answer all of your questions? Are there any open questions? So I want everything to be clear. This is the paradigm. That's why you choose a training data. That's why you choose a validation data. That's why you choose a test data. And once you're happy after the performance of your model on the test data, you put it in production. And usually these test data, there are these competitions that you submit your model. They're not going to give you the corresponding YI double primes. They're going to hide the corresponding labels, but they're just going to report your accuracy. So that's a fair way of doing the competition. Now you know why you do training, validation, testing. And this model that I'm writing here, if you choose your number of layers to be 1, you're just doing logistic regression, which is a classical statistical algorithm, statistical model. So a 1-layer deep multi-layer perceptron is going to give you logistic regression. And because it's 1 layer, it is linear, you can study the parameters. You can say, because the weight on this variable is higher, this is probably having the most impact on the predictions. And then you can study it. But as soon as you become deeper, it's harder and harder to study these weights and biases. You just look at the predictions of your model, you make sure it's okay, and then you put it in production. Any other questions? Was everything clear? So this is going to be the entire paradigm for whatever that we are going to be doing next. You're always going to have this paradigm. There are some hyperparameters. There are some parameters. There is some learning going on. There is some validation going on, some testing going on. You always have this paradigm. This is for a simple model and a simple data set. Next, we are going to change the data set to be more complex, like looking at images, speech, text, and making our models more complex using convolutional neural networks, using recurrent neural networks, LSTMs, transformers, MLPs, etc. But this is always going to be the paradigm. I think it's a good time to stop. For those of you who have questions, you are more than welcome to stay and ask. And for those of you who want to leave, you can leave. And the question is, the order is always train, validate, test? Yes. You first pick your hyperparameters, then you train your parameters, you validate. Basically, you try to come up with the best hyperparameters, and then you test it. You put it in production. Next.
So would it be good to think of alpha just abstractly as the network architecture?
Exactly. Yes. And there are some other details. For instance, what is going to be the learning rate when you're doing gradient descent? Those could be part of your hyperparameters. So what I want you to do is watch the next video, on the next slide. And there's a question from Pragna, but we need alpha to train. So don't we have to validate first? So it's going to be, you pick alpha, then you're going to know what is going to be the sizes of your beta. Then you're going to do training. It's going to give you some performance on the validation. You change alpha to be another alpha. You do another round of training. You come back, you change alpha, another round of training. And this for loop, once it is done, it's done. You find alpha star and beta star. And then it's game over. So there is going to be a for loop on alpha. There is going to be another for loop on beta. And the for loop on beta is the inner for loop. For alpha in a set, for beta in another set, do the training. Okay, any other questions?
Thank you.
Yeah, sure.